Thermodynamics, kinetic theory, and internal energy. Questions to ponder. What is a kinetic theory and how is it related to temperature? What is the root mean square velocity of a molecule? And what is internal energy and how is it related to temperature? So let's explore kinetic theory and how it relates to temperature. Recall that we look at a system in two different ways. We can look at the macro system here with its volume and number of moles and pressure and temperature, or we can look and zoom way in and visualize these molecules with their own individual masses and their own individual velocities. The one big equation here, very important equation, that relates our micro world to our macro world here. In other words, masses and velocities of individual molecules to temperatures within this macro system. This is called the kinetic theory. And there's quite a lengthy derivation of this particular equation. You can find that in most textbooks that you look at under kinetic theory. Rather than do that, I wanted to take a specific look at how these are related. So again, to understand how the micro world is related to the macro world here, we are looking at individual molecules of a gas here. So that would be a single gas molecule, and that would be the average speed of this molecule, and of course this is the molecule's translational kinetic energy. In the derivation, they use a process called the root mean square process to find the average speed of molecules, since it would be impossible to find the speed of one particular molecule, and it's really the average that's important. So this is an average speed of one particular molecule, and this would be the temperature of our system, and that's Boltzmann's constant. So this is our equivalency between our macro world and our micro world.
So this is a very nice illustration of the small particles going super fast, the medium-sized particles going medium speed, and the big particles going slowly, but they all have about the same energy. To get energy for a small particle, it has to go very fast. It's 1/2 mv squared. So it makes up for the small m by its large v squared.
So let's take a look at a problem right away using that last equation to see if we how it could be used to solve for the kinetic energy of a particular molecule. And so if we have a gas that has a temperature of 20 degrees Celsius, what would the average kinetic energy of that gas molecule be? Take a minute and give it a try. It's really quite simple with a plug-in method, and come on back. So how did you do? Again, it's pretty much a simple plug-in problem if you realize the average kinetic energy was the 1/2 mv squared all lumped together. And that, to make it equivalent to temperature here, we simply plug in the temperature of 20 degrees C. Of course, we have to convert that to Kelvin since the Boltzmann's constant is in Kelvin here. So 20 plus 273 Kelvin is 293 Kelvin. And then it's simply a plug-in using Boltzmann's constant here. And we can see that the average kinetic energy of one of those gas molecules is quite tiny, because again, a gas molecule and its mass is quite tiny. So we might want to know what the average speed of those gas molecules is, and this is quite interesting. They're tiny masses, so they must have some pretty high speeds or velocities. So using our equivalency equation here for the kinetic theory, we can solve for what that average speed would be, and doing a little bit of algebra, multiplying through by 2 here, and then dividing through by the mass of one molecule, and then finally taking the square root of both sides, we get the average speed of one of these molecules of gas. And again, that averaging process is called the root mean squared. So this is called the root mean squared velocity or speed of one particular gas molecule. And that's our equation. VRMS is equal to the square root of 3 times the Boltzmann's constant times the temperature in Kelvin, again divided by the mass of just one of these molecules here. And again, that's the RMS, or root mean squared speed. Let's see how we can use it in an equation, in a problem. Before we move on, since this root mean squared speed is related to just the mass of one molecule here, let's do a quick review of how we can find the mass of a particular molecule. So if we can find the molecular mass, and you can pause the video and recall how to do that, once we know the molecular mass, we can simply multiply that molecular mass by the atomic mass unit of 1.66 times 10 to the negative 27 kilograms, and that'll give us the overall mass of a particular, or the actual mass rather, of a particular molecule. So one molecule of carbon dioxide, for example, is 7.31 times 10 to the negative 26 kilograms. So maybe pause this video and review how you can find actual mass before doing the RMS speed problem. So here is our problem for finding the average molecular speed, or RMS speed. And so the average speed of two common air molecules, oxygen and nitrogen, at 24 degrees Celsius. Remember, you're going to have to find the actual mass of these molecules first before you go on to solving for the RMS speed. Good luck, and come back when you're done. So how did you do? Again, finding the actual masses here. The mass of one oxygen atom is 16 atomic mass units. So since there are two oxygen atoms in an oxygen molecule, 16 times 2 is 32 atomic mass units for an oxygen molecule, times the atomic mass unit itself, and that gives you the mass of one oxygen molecule. And likewise, do the same process to find the mass of one nitrogen molecule. Then it just simply becomes a plug-in problem using those two different masses, Boltzmann's constant, and of course we have to convert 24 degrees Celsius into Kelvin. So 24 plus 273 was the 297 used in these problems. And cranking all of that out, we get these incredibly high speeds. And it makes sense that these tiny molecules are moving at really, really high speeds to develop the kind of energies that they do with these temperatures. Next, let's take a look at internal energy. Internal energy, U, we have to be careful because we used U before as potential energy in mechanical systems as mgh and so forth. Internal energy is a little bit different. Internal energy is related to the kinetic energy of these molecules. So that's one thing. When you're looking at thermal systems and you see the symbol U, be very cautious. That's not the old potential energy that you were used to in mechanical systems. And it's wrapped up primarily in these kinetic energies. So if I was going to find the total internal energy of this gas inside this container here, I can't just look at one average molecule's energy. I have to take all of the molecules that are in that container and multiply by each of their individual kinetic energies here. And so translating that into our macro system, if I take all of the molecules and take the 3/2 kT for our translator here, then we would have found the total internal energy U using this equation. And we can translate, since nkt is equal to nRT, depending if we have the number of molecules or if we have a number of moles, these two are equivalent. So if I have a system with a certain number of moles, I will use this equation. If I have a system with a certain number of molecules mentioned, I will use this equation. And those are our internal energy equations. So here's a sample problem using those internal energy equations. If I have 10 moles of water, H2O, at a temperature of 80 degrees Celsius, what is its internal energy? And then if I have a lot of those water molecules at that same temperature, so we can look at this same problem two ways, one using moles and one using molecules. So pause the video, give this a go, and come on back when you are done. So we have our two internal energy equations, one using moles and one using molecules. And this is simply a plug-in type problem. So we have 3 halves, which is 1.5, times the 10 moles, times our gas constant here of 8.31 joules per mole Kelvin. And then, of course, we had to translate 80 degrees, add 273 to 80 to get the 253 Kelvin. And plugging all in, we get 44,000 joules. So that's quite a bit of water, and that's quite a high temperature. And so that's an awful lot of energy stored in that bunch of water molecules there, or moles of water. Looking at in a molecular way, it's really simply a plug-in problem as well. And plugging in 6.022 times 10 to the 24th molecules with Boltzmann's constant now, we get the same energy. So really 10 moles of water is equivalent to 6.022 times 10 to the 24th molecules. And since those two are equivalent, the energies are the same internally. So hopefully you can answer your questions here. What is kinetic theory and how is it related to temperature? That's our microsystem related to our macrosystem. What is the RMS velocity? Again, equating these and solving for V. And then what is the internal energy and how is it related to temperature? Recalling that internal energy is not like the U in mechanical potential energy. So, scratch his parting idea. And keep up that speed on your quest for continuous improvement.